Hi, welcome back to Math 112. Today we're going to talk about section 6.5, which is all about modeling with trigonometric equations. So let me give you my screen here so you can see. All right. So what we're going to do, as soon as I make it so you can actually see, we're going to just go through some examples here. So this is an example from section 6.5 of your text. And what we're told is that an airplane needs to fly to an airfield located 30 miles east and 200 miles north of its current location. At what heading should the airplane fly? In other words, if we ignore air resistance or wind speed, how many degrees north of east should the airplane fly? So let's start by visualizing what's going on. My airplane is located right there, okay? And I want to get from that spot to a spot that is 300 miles east and 200 miles north of my current location. So in other words, I'm trying to figure out how to do that. And here's what I know. I know that this distance here is 300, and this distance here is 200. So what I really want is the measure of that angle, theta. Okay, well, what I have here is a right triangle, yes? And I remember that the tangent of any angle in a right triangle is equal to the length of the side opposite divided by the length of the side adjacent. So if I know that, then I can find that angle by taking the inverse tangent of both sides, and I'm going to simplify 200 over 300 to 2/3. And I can use Desmos or your TI calculator, whichever one is easier for you. I'm going to use Desmos. Make sure I'm in degrees because airplane headings tend to be in degrees. So let's put ourselves into degrees. And now I'm just going to take the inverse tangent of 2/3. And Desmos tells me that I should fly at a heading of 33.69 degrees. Okay, so we've applied what we know about right triangles and trigonometric functions along with the information we know about inverse trigonometric functions to solve this equation and give my pilots a new heading. All right. So let's do another one. This one's going to be a little bit more complicated. Here we're going to talk about an object attached to a spring. Now, remember what happens when we stretch a spring? When we stretch a spring and we pull backwards and we let something go, what happens? It bounces, right? So if something bounces, what we're really talking about here is an oscillating function. This is going to be a sinusoidal function that will describe the movement of this object. So let's think about how we're going to write this equation, because what this says is we've got an object connected to the wall with a spring that has a natural length of 20 centimeters. The object is pulled back 8 centimeters past the natural length and released. The object oscillates 3 times per second, and we want to find an equation for the horizontal position of the object, ignoring the effects of friction. So we know, because we've played with springs in real life, we know that a spring its oscillations will slow down over time. That's the effect of friction. We don't have friction going on here because it's told us we can ignore it. So we're just going to write an equation without worrying about friction. We will get to friction later. Friction creates what's called damped harmonic motion. We're just going to write a continuously oscillating function that never slows down. So let's talk about, first of all, finding the equation for the horizontal position. So let's think about this image, this guy right here. At rest, before we do anything, this distance is 20. Okay? Now, what happens is somebody takes this cart and stretches it out so that it is a total of 28 centimeters. So the difference here is 8. Now what's going to happen is the cart will bounce between 8 centimeters beyond the spring and another position in here that is 8 centimeters closer. Okay? So what we're talking about is the distance that the object is from the wall. That's going to be my y coordinate. So I'm going to make a sketch here. So I'm putting in a dashed line that is not the x-axis, is going to be my midline. And my midline will be the resting position or the equilibrium position of my spring. So this midline is actually y equals 20. Okay? Now, my maximum distance out is going to be at 28. So this top curve that I'm putting in right now is going to be the top of my oscillating function. And the minimum distance is 8 less than 20, or 12. Now my function starts at the midline because my cart starts at the resting position. So it looks like this, and then it goes out and bounces back. Okay, so that's the basic sketch of behavior. Now I've got to do a couple more things. My x-axis is going to be in time. So my x-axis is down here somewhere, and that's going to be in seconds. So I know that the cart oscillates 3 times per second. Now if it oscillates 3 times per second, that means, so it oscillates 3 times per second. That's what we call the frequency. Now the frequency is actually the reciprocal of the period. So that means that my period is 1/3. We're going to work in radians here. So that means my internal multiplier. So I've got, if I look at my function here, I've got a sine function because it starts at the origin and goes up. So it's going to be sine function. I need an internal multiplier, and that internal multiplier is the natural period divided by the observed period, or 6 pi. I do not need a horizontal shift because I go through the origin. I do need a vertical shift of 20 to get me to my midline, and I need to pay attention to my amplitude. My amplitude is 8. So if I graph that, put myself back in radians, y equals 8 times the sine of 6 pi x plus 20. Okay, so that's pretty obnoxious, but if I play with my settings a little bit here, so my y-axis starts at 0, our x-axis starts at 0, goes to 9, and I know that I don't need to worry about anything below 12 or above 28. Okay. So let's change that to 3. That's good enough. Okay. So that gives me, does that look right? Let's see, we oscillate 3 times per second. Yes. Okay. So that actually gives me 9 periods. I don't even really need that many. So let's just go to 1. All right. There we go. So that matches what I expect. And so that will be, this is my equation that describes the motion of my cart. So we did that. Now here's the second question is, how much time during each cycle is the object more than 27 centimeters from the wall? So what we're asking is, if I think about another line that goes, so if I draw a horizontal line right here, and it's at 27, what I want to know is, what is the distance between those 2 points? So what I'm really saying is, find the first 2 positive solutions to the equation (27 equals 8 times the sine of 6 pi x plus 20. So let me make some space here so that I've got some room to write. So I'm gonna make all this go away, because we're done with that sketch now. Oops, not all that. Here, I'll do it this way. Little whiteboard magic here. Okay. Now I'm going to, actually I don't need this either. Okay. I'll move this up. Okay, here we go. So what I'm going to do, so what I said is, I want to know, where does this function actually equal 27? So I'm going to find the first 2 positive solutions to the equation 27 equals 8 times the sine of 6 pi x plus 20. So first start by isolating our trigonometric function. So we're going to subtract 20 from both sides. So we end up with 7 equals 8 times the sine of 6 pi x. Now divide through by 8. So we get 7/8 equals sine of 6 pi x. Now remember how I like to do these. I'm going to make a substitution so that theta equals 6 pi x. So I've got 7/8 equals sine theta. Take the inverse sine of both sides of that equation, and we get theta equals inverse sine of 7/8, which Desmos will tell me is 1.065. That's my first theta. How do I get to another? I know I've got to have 2, so how do I get to another angle that has that same sign? Well, envision your unit circle. It's not a very good circle. That's a better circle. Where is 1.065 on my unit circle? Well, it's less than 1.5, which means it's less than theta over 2, so I'm somewhere in quadrant 1, right? So my next angle will be in quadrant 2, so my theta 2 will be pi minus 1.065, which is 2.076. But now remember, those aren't my answers. Those are not my x's, because theta is 6 pi x. So this means that x equals theta divided by 6 pi. So my first x is going to be my first theta divided by 6 pi, which is, so 1.065 divided by 6 pi, which is going to be approximately equal to 0.0565. And the second one is 2.076 divided by 6 pi. Or 0.1101. Now, those are both seconds because my x's are seconds. So the time between them is just x2 minus x1, which is 0.1101 minus 0.0565, or 0.0536 seconds. Okay? Now, we can check our work on Desmos fairly easily by just adding this line y equals 27 to my graph. And notice here, Desmos will give me the coordinates of my intersection point. And it gives it to me as 0.0565 for the first one, and 0.1101 for the second one. That's a great check. On the exam, I'm going to want to see your work to know that you know how to do this problem. Okay? So Desmos helps, but it's not the answer to everything. It just helps. It's a tool. Okay. If you have any questions, please, please, please be sure and let me know. All right, let's do one more. And this is actually not an uncommon situation where we've got a circle, a gear, a circular gear, driving a horizontal piston. This happens a lot in a lot of different motors and engines and in industry. So we've got a rigid rod with a length of 10 centimeters attached to a circle of radius 4 centimeters at a point A. Point B, at the other end of that rigid rod, is able to freely move along the horizontal axis driving a piston. If the wheel rotates counterclockwise at 5 revolutions per second, we want to find the location of point B as a function of time. And we want to know when will that point B be 12 centimeters from the circle. So we want to know, first thing we want to do is describe the motion of that piston as a function of time. And if you think about what's going to happen, as this circle rotates, this rod will move and it's going to drive that piston in, right? So it's going to move it in and out in an oscillating manner, just like our spring. Okay? What is going to drive the period of that oscillation? It's going to be the speed at which the circle rotates, speed at which the wheel rotates, yes? Okay. So let's start with what we know is rotational speed. So we know that the wheel rotates at a speed of 5 revolutions per second, which means, so each revolution is 2 pi radians. So my rotational speed is 10 pi radians per second. So that is my rotational speed. So after t seconds, my wheel will have rotated 10 pi t radians, right? Okay. We care about that because what we need to do is express the position of this point as a function of time. So we can start with the coordinates of that point are the radius times the cosine of the angle and the radius times the sine of the angle, right? This 10 pi t is my angle theta as a function of time. So I can now write the coordinates of that point as 4 times the cosine of 10 pi t, comma 4 sine 10 pi t. Now we like that because once I have those coordinates, then I have the ability to construct this right triangle. And I know the coordinate of, so I know this, I know x and I know y, which means I know that distance and I know that distance, right? And I know this distance because it is the hypotenuse, it's the rod, yes? So once I know that, then I can use the Pythagorean theorem to figure out some other things. So I know x. Actually, I don't know x. What I know x, but I don't know this distance b. But I do know this distance y. That distance y is 4 sine 10 pi t. So based on the Pythagorean theorem, I know that 100, or 10 squared, is equal to my base squared plus my y squared, which is 4 sine of 10 pi t. So I actually know that my base squared is going to be equal to 100 minus 16 times the sine of 10 pi t squared. So my base is going to be the square root, sorry, technology is helping, square root of 100 minus 16 times the sine squared of 10 pi t. Now this base is almost the x-coordinate of my rod. What's missing? Well, it's that distance right there, right? And that distance is my x-coordinate. So my x of my rod, which I'm going to call x of t, is equal to the x-coordinate of my point, which is 4 cosine of 10 pi t, plus my base of that triangle, which is the square root, yes, of 100 minus 16 times the sine squared of 10 pi t. Okay, that's my equation that describes the movement of my rod. Okay? All right, let's make some space so we can finish out this problem and find when the point will be 12 centimeters from the center of the circle. So my circle is centered at the origin. And so that means that if I want to know the time when the rod is 12 centimeters from the circle of the origin, that means I'm really solving the equation 12 equals 4 times the cosine of 10 pi t plus the square root of 100 minus 16 times the sine squared of 10 pi t. All right, your textbook has got a really nice detailed description of how to solve this using algebra and some inverse trigonometric functions. And I encourage you highly to look at that. What I'm going to tell you is that that's a fairly time-consuming process, and you should know how to do it, but we have tools. So what we're going to do is we're going to go to Desmos, and I'm going to make my Desmos window a little bit bigger. And we're going to type in on the one hand, on one line, y equals 12. Okay, that's the left-hand side of this equation. And on the other side, we're going to type, or on another line, we're going to type y equals 4 times the cosine of 10 pi. Now, instead of t, I'm going to use x. Okay? Plus the square root of 100 minus 16 times sine squared of 10 pi x. Okay, and I'm going to zoom in because I really just want to know the first time that the rod, well, is that what I want to know? We'll talk about this. Let's start with the first time my rod is 12 centimeters from the center of the circle, and it's right here at 0.02851 seconds. Okay, so now I'm going to shrink my Desmos window back down. So the first time that the rod passes through 12 centimeters is 0.2851. Wrong. There's a 0 here. After the cycle begins. And then again at 0.1715 seconds. Now, remember though that it does this again and again and again. And so the difference between that first point and the third point is 0.2 or 1/5 of a second. So the way we write that is we write plus 0.2 K seconds. So if every 0.2 seconds, every 1/5 of a second after that. And same thing here. All right? Okay. I encourage you, if you have any questions about this, to take a look in your text, because this is example 7 from your textbook. And to let me know if you need some help. And real quick, I just want to share with you an animation of what's going on here. Now, we're looking at a horizontal. This animation is a vertical. And this link is in your textbook, so you can take a look at this for yourself. But this is the situation that we are talking about. Just turn it sideways, 90 degrees. All right, I look forward to talking with all of you soon. Have a great day and good luck with this homework. Let me know if you have any questions. I'll talk to you again soon. Bye.